So when we talk about MED systems, then we are limiting the top brine temperature to 70 degrees centigrade because the seawater is sprayed on the outside surface of the tubes in the tube bundle. Cleaning is not easy to do. You cannot do it while the system is operating. So in order to clean it, you have to stop the system, you have to clean it, or at least replace some of the bundles and operate it again, and then you can clean them. So the point is to avoid this issue of corrosion, scaling, fouling on the outer surface of the tubes. You try to keep the temperature down so that you don't have scaled surfaces. You can see here in a system like in the figure, we are talking about a top temperature of about 69, where the bottom temperature is about 49. You have a certain range, if you are, and a temperature on the other side, at the low side, which is greater than the seawater temperature by about 10. So we're talking about 40. So between 70 and 40, you can put a certain number of effects. And this is your limit. You can do some additions to it if you have, for example, operation with nanofiltration associated with an MED system. Then through the nanofiltration, you can get rid of the ions that result in scaling. Accordingly, you can increase this temperature from 70 maybe to 90, and then you can add more effects. Adding more effects is the most influential improve the MED performance, because the performance ratio is basically proportional to the number of effects. You have 4 effects, then your PR is closer to 4, 8 effects closer to 4, 16 effects is closer to 16, and so on. So the MED plants usually operate at a top temperature of about 70. Another, you can increase it. There are trials to increase it by one of the manufacturing companies of MED system is a Japanese company called Sasakura, and another Korean company called Doosan. What do? They can increase the dose of chemicals added to the seawater after passing by the condenser so that they can be able to increase the top brine temperature. But again, it's costly. The other thing is some trials that have been done to connect the MED process or MED system to another system from the low temperature side, in which you can in vacuum. So you are basically extending the low side of it. Extending the low side have a very good feature to worry about scaling at all. And there's some work that has been done in King Abdullah University of Science and Technology, KAUST, where they have a project there that they call MEDAD. MEDAD is where they are adding an MED system into an adsorption system, adsorption cooling system. So it becomes for desalination and cooling, and they can operate it up to a lower temperature of about maybe 15 degrees or so. So they have extended the low side of MED system and increased the number of effects over there. The experimental setup that they have is only having 4 effects, but they operate the whole 4 effects either in a high temperature side or a low temperature side, because it's basically there for testing. The goal of this system can be reaching a value of 14, for example, and as we know, it is directly proportional to the number of effects. In some of our visits to some desalination plants, actually we have seen we have been first introduced to a place in Spain called Almeria or Almeria. Almeria, they have desalination facility that is busy operated by solar energy. They have so many systems to operate by solar energy. Some of them, like what you see here, they have a field of solar collectors. The solar collectors are basically heating oil. The oil is being heated to high temperature of about 400 degrees centigrade. And this oil is being, definitely it is being stored. And the oil has been passing in heat exchangers versus water. Water is converted into steam. Steam is operating steam turbines. So it is running basically on a Rankine cycle. And then after that, steam at the low pressure turbine is extracted at a temperature of about 70 to operate an MED unit, which is basically vertically where the effects are placed on top of each other, as you can see it here, and it can operate to produce water. So you have a system here, which is operated by solar energy, and this system basically is producing power, electric power through the generator, and steam is taken here to operate a desalination system. The issue of having desalination and electric production is the of the big desalination plants, like what you see here in Azazia, Khobar, and in Jubail and in Marafiq. Basically, they have a combination of a power plant, and it's a dual cycle power plant, like a gas turbine and a steam turbine. And then, because steam is there, they connect to it desalination systems. The desalination systems that we have could be either multi-stage flash desalination, as we shall be talking about in our next class, or MED system like what happens in Marafiq Jubail. Yeah, what we need to do basically with this MED systems that we are having in our course is evaluation the performance with or without vapor compression. We have seen the vapor compression to be either thermal vapor compression through using a thermal vapor compressor or ejector, or a mechanical vapor compressor. And then there are actually new systems of MED desalination systems that are operating not only with mechanical compression, but the problem with mechanical compression is that you have vapor that is leaving in the last effect. We can see it here in the figure. The last effect vapor is taken out of here, and all the vapor is routed into a mechanical vapor compressor. The compressor compresses the vapor from the last effect pressure to the first effect, a little bit more than the first effect pressure, so that that superheated vapor is going to enter into the tubes and heat the seawater, which is distributed here. What arrangement? The seawater comes, it is distributed in two heat exchangers, a brine feed heat exchanger preheater and a distillate preheater. So the seawater is being distributed in both of these to be heated from T cooling water to TF. And then the feed is taken out of these units and is distributed in parallel. Steam is coming in, it heats the seawater to the saturation temperature, and part of it will evaporate. The vapor will be taken out of here. It will be used for as a source of heat in the next effect, where it will condense, heating and the issue here, or the process continues until the last effect, where the vapor leaving the last effect is taken, all of it, as an input to the mechanical compressor. The mechanical compressor can be connected into a diesel engine, or it can be connected just to an electric motor that can be operated by a photovoltaic system. Sorry. Then this superheated vapor is taken as the source of heat, and the cycle arrangement in terms that it is self-contained. You don't need to connect it to a power plant. All you have to take it is that you have a unit that you can move it anywhere, as long as you have mechanical work input to the unit in terms of diesel engine or whatever, or even electric motor. Wind turbine is another option, but you don't connect it directly to the wind turbine, because the wind turbine is not operating continuously. Whenever there is wind, it will operate. The speed will increase. If we have a strong wind, the speed will decrease. A wind turbine that's connected to a generator to produce electricity, and then the electricity runs the compressor that we have here. The problem with this system is vapor compression requires a lot of energy because you are compressing vapor. And as you have seen in the equation that you have that we looked at in terms of the power calculations for the compressor of a single effect system, or definitely a multi-effect system, that the equation is a function of the suction pressure and specific volume. The specific volume of vapor is large, and accordingly, the work required to operate it is large. So in terms of power consumption, this is an energy consumer. It consumes a lot of energy compared to other desalination systems. This is why people have thought of other ideas instead of using a compressor other systems. So the whole thing here remains the same, except for the compressor itself is going to operate with a different systems. Absorption, for example, is one of them, vapor absorption, or adsorption. Absorption is al-imtisas, so that you have some sort of a strong liquid desiccant like calcium chloride or lithium bromide or lithium chloride. It absorbs the water vapor at a low pressure, so that the water vapor is as if it dissolves in that solution. And then you pump the solution to a high pressure through a pump, and a pump definitely requires much less power than a compressor. And then at high pressure, you heat it by solar energy so that the water vapor is separated from the solution, and you take the water vapor here as a source of heat. And then the solution is taken as a strong solution, and you pass a certain amount of vapor to it, and then the cycle of the absorption is repeated again. You can read about the absorption in chapter 3 of the book if you like, and it's a very interesting kind of process. We tested this process with different systems. We tested it with membrane distillation, we tested it with multi-effect desalination, we tested it lately, or some of our group has tested it in HDH connected to an absorption system, and it seems that it's giving you a couple of effects. One of them is cooling effect for air conditioning, and the other one is desalination effect. For a mechanical vapor compression system, each one of the effects is going to have a vapor space, mist eliminator, condenser or evaporator tubes, spray nozzles for the seawater coming, and place for collecting the brine that does not evaporate. The vapor moves from left to right in our case here, because as you can, an additional amount of vapor that goes to the second effect, and then it will condense, and meanwhile it will generate vapor that will go to the third effect. So vapor is moving from effect to 1 to 2 to 3 to 4. It's moving basically in this direction, whereas the seawater is going perpendicular from up to down through the sprayers. So we're talking about here a parallel flow system, where horizontal flow of the vapor from left to right, vertical flow of the seawater which is being sprayed after being distributed equally between the effect. In this unit, the vapor leaving the last effect is going to the compressor right away. But what we do, we preheat the seawater by the brine which is being rejected. It's at relatively high temperature. We make use of it for preheating the seawater. And the distillate that we are connected, it's also making use of in preheat. This is a description of the process. I just mentioned it a while ago, and it's been repeated since we talked about that earlier. And flashing would be there. The system that I showed a while ago has flash boxes. You can see it here, so that the distillate that condenses inside the tubes it goes into a flash box. The flash box normally is connected to or it's at the same condition in terms of pressure as the effect that it's connected to. Here we have compressed superheated vapor. The vapor will come in, it will condense, it will desuperheat and then condense at a constant pressure, which is that pressure of steam coming here. This is higher than the pressure of effect number one. So that when you get that liquid distillate to a flash box of a lower pressure, some flashing will occur. You take the flashed off vapor in addition to the vapor which is coming by boiling from the effect, and both of these are going to be the source of heat for the next effect, and the things being repeated here. The difference that we have here compared to the previous installations of MED systems is that the number of flash boxes here is equal to the number of effects. Because for this effect, for this system, the first effect has a flash box. In the previous ones, we did not have flash box with the first effect. Why? Because in the previous installations, we had vapor coming from a power plant. So it's not our vapor, it's not our product. You condense it and you turn it to the power plant. But here, the vapor that we are using as a source of heat is basically our product, which is coming from the last effect. That's what. So we talked about the process already, which is basically is given in sort of summary in this slide, and a modification to the system is being done through, but not having a parallel effect, but a parallel cross effect. And the parallel cross arrangement is going to have, leaving the bottom of one effect is entering into the bottom of the next effect, which is at a lower pressure, so that it doesn't add additional quantity of flashing, and you take that flashing as your, I mean, it's an added vapor which is coming to the productivity. Khalid, you have a question? Go ahead, please.
Yes, good morning, Doctor. The
Good
flashing
morning.
box, can you hear me? Yeah.
Yes, I can hear you.
So the distillants that come out from the flash boxes, can we just take it out as a distillant instead of preheating it or make it as a source of the second effect, as a source of heating, I mean?
In the one which is coming by flashing, yes, you can. But the point is, why are we taking it here to the next effect?
To make
Because
the
it's
sweeter.
vapor. Yes, and the vapor needs to condense. So to condense it, let's make use of the latent heat of condensation. So this is the kind of benefit that you are having here. So instead of having a source of energy or a source of heat, which is basically the boiled off vapor in the previous effect, and the flashed off vapor at the bottom of the effect, which is coming from the brine of the previous effect, but you add to it whatever you are getting from the flash box as well. So you are adding the quantity of vapor, which will condense inside the tubes, and the condensation input heat is going to be the total mass flow rates, this one, this one, this one, into HFG. So this is going to produce a little bit more heat that will help in preheating the water and generating additional quantity of distillate here, vapor.
Again, Doctor, can we use flash
You may take,
for single effect evaporation?
no, because in the single effect evaporation, your source of steam is coming from outside. You can use it only mechanical, because for the mechanical, you are taking the vapor that you are producing, and it will be the source of input to the compressor. The compressor heats it to a high temperature, and then it can join. You may have a flashing box, and then the vapor leaving the flash box can get into the condenser. Or there is no condenser, there is a distillate preheater, so it will just, it's not useful there. It's only useful whenever you have a multi-effect desalination, so that you are making use of additional vapor to condense in the next effect and produce more distillate. So I don't see the effect unit. It becomes only useful whenever you are talking about a multiple effects, where energy leaving one effect is the source of heat for the second effect. Did I? I'm not sure if Khaled is still with us. It seems that
I am, Doctor, because I don't know, there is a loss of connection. Is it in my side or in your side? I don't know actually.
I'm not sure. I'm not sure. So did you hear my answer to your
Yes, yes,
question?
yeah, I did, Doctor. Thank you so much.
Okay, fine. Good. Then when it comes to the analysis for the system, then basically we take one unit. We have done that before. This is just repeated here for sake of just reminding you that we are talking about an MED parallel cross unit, and the parallel cross with flash boxes. It means that whatever is going to enter to any effect as distillate, as vapor, it will be the vapor formed in the previous effect, the vapor flashed at the bottom of the previous effect, the vapor coming from a flash box, and all of these are going to enter to the tube side. They will condense and generate vapor, which is DI. It will, this brine, which is coming from the previous effect at a higher pressure, it will enter into a lower pressure here. Part of it will flash, which is the small d. So capital D is by evaporation, small d is by flashing, and the D dash is coming here due to the flashing, the flash of vapor in the flashing box. Then these two quantities plus this quantity will be the input to the next effect as similar to this one. The brine is coming from the previous effect at a higher pressure and temperature compared to this effect. It will flash off here, and then we have BI, and BI here is less than BI minus 1 by these two quantities, capital D and small d, because part has formed by evaporation and part has been formed by flashing here. And of input is being here, and we have Fi, which is the flashing, which is, sorry, the seawater that has been flashing. We have Fi coming in, Bi minus 1 coming in, and whatever the mass leaving is going to be Bi leaving, and then capital D plus small d leaving. I'm talking about the mass balance for the system. When it comes to the energy balance, then each one of the components I mentioned is coming with its own enthalpy. In addition, definitely to Di minus 1, Di minus 1, D dash I minus 1 multiplied by HFG, which is the latent heat of condensation for this. And that's basically what's been shown here. This is, we have feed coming in, we have brine from the previous effect coming in, and then we have a quantity of distillate, which is a combination of the formed vapor and the flashed vapor, and then the brine that is rejected from this effect. The distillate is free of salt, so the salt balance is written here based on this equation. Rejected brine salinity can be written as well as a function of the temperature. This has been given an al-Dusuqi in his book. You can find this equation in the appendix. The book, which is there on the blackboard by al-Dusuqi and al-Tuni, they came up with this approximate how to do that. We know how to obtain it by the mass balance. And for the, we have seen that for the parallel, we have seen this slide before, and we've talked about how the balance can be done. We are just looking at here at slightly more details, that this is the energy input to the unit, which is basically this quantity entering a saturated vapor, leaving a saturated liquid. So this mass multiplied by the energy the HFG is lambda here, the vapor that comes to condense here. This is going to heat the feed from TF to TI, and part is going to evaporate here. Actually, in this specific part, it's not only that part that will evaporate, but there is an additional quantity here which is missing in that expression, and this quantity should be the flashed off vapor which is coming from the bottom of the effect. That's just again comment on the equation. The boiling point elevation is less than the temperature of the effect by, the temperature of the vapor is less than the temperature of effect by boiling point elevation. And as a matter of fact, if you need to be very accurate, as we are moving from one effect to the other, it's not only the boiling point elevation that makes a difference. Upon condensation, there is delta P, there is delta T due to pressure loss, there is delta T due to the transmission line, and there is delta T due to the loss of pressure while condensation. So the pressure loss could be pressure loss in the demister or in the pipelines, and these are small to consider. But if you need to go for a very, very accurate in your work, the amount of vapor that comes inside the flash box can be given by that expression. We have seen this expression last time, and normally the temperature leaving the flash box can be given as the temperature of the flash box or the effect minus non-equilibrium allowance expression. In our simplified analysis, we just consider the losses to be the boiling point elevation and the delta T, which is between any effect and the other one. But sometimes in a problem, you have something which is called thermodynamic losses. The thermodynamic losses basically is being taken care of the non-equilibrium allowances and this kind of delta T that we have due to the transmission lines, due to the demister, and due to the condensation. In terms of areas, we calculate the area and we distribute the area as two parts. One of them is due to the sensible heating. We have taken an example of this and we have calculated the area due to the sensible heating to be small, but if you have a larger temperature difference, then this sensible part cannot be neglected. Definitely the latent part will remain always the bigger, but sometimes you can have this value exceeding 10%, and in that case, you would not tend to neglect it. We talked about this before, how to calculate the log mean temperature difference for every effect, and the equations for the compressor power is being given here. And after that, gamma can be calculated basically either as Cp over Cv, as you have seen earlier, or again, Al-Dessouky came up with this kind of empirical formula to calculate the value of gamma. I personally prefer that we go for the vapor and see what is the value of the Cp, what's the value of gamma. The preheaters, again, we have the seawater is being divided, not equally between the two preheaters. Portion of it is going to go for the distillate preheater. The other one is going to go for the brine preheater, and then they are going to make an energy balance for the whole unit as a whole. Then this is your equation here. QH is M feed Cp TF minus T cooling water. But we know that part of that MF has been heated in the distillate preheater and the rest has been heated in the brine preheater. But this is some sort of an overall energy balance for the two heaters together. And this is the details. Part of it is in the distillate preheater, part in the brine preheater, and then both of the distillate and the brine are leaving both heat exchangers at a constant temperature T naught, which is basically an assumption, because in reality it is not necessarily a same value, but this is, we do that for the simplicity of our calculations. And this is basically the area of the distillate preheater. And similarly, a similar equation is written of how to calculate the area for the brine preheater, which is being given here, and the log mean temperature difference for each one of them is being expressed here. So that's something that we have done before. That's why I'm going fairly quickly across these slides. Now there is some sort of let's call it a little exercise that I want. And the exercise here is basically considering a layout of a multi-effect distillate unit. And the unit here is operating with vapor compression. What we have basically is what we have basically here is 4 effects. We have a brine preheater and a distillate preheater. We have flashing boxes, 1, 2, 3 boxes, and we have vapor, which is coming from the flashing boxes, and the vapor going out of the flashing boxes is entering into the next effect with the foamed vapor. So that's it makes additional vapor, and we have parallel cross arrangement. So the brine leaving one effect is entering to the bottom of the next effect for additional flashing. Now, what I want to take, I'll leave you for about 2 to 3 minutes so that you can look again carefully into this figure and try to think of these question marks that hello, can you hear me? It seems that I lost the connection and then it was restored again.
Doctor, I believe from the start of the lecture, I think many of us have, there is a connection issue. It's go in and off, and your voice is not continuous. I was thinking because of my internet connection, but there is one of my colleagues here said
Oh,
Osama and Khalid. No, I mean Khalid. He also confirmed that. I think from your side, I believe.
it looks what about now? I mean, can you hear me clearly now? Is it better?
Just a bit. 3 seconds ago, your voice was interrupted. Actually.
What about now? Is it better? Is it steady?
Now it's okay.
Okay, so anyway, I'm sorry about this. It seems that I had an issue with the connectivity, but anyway, you should be able to hopefully to find this what I just discussed on a recorded lecture of today. So again, I'll talk about what we have right now in front of us is an MED unit with vapor compression. We have flashing boxes at the bottom or connected to effects number 2, number 3, and number 4. We have a couple of preheaters, and the vapor that leaves the last effect joins the quantity of vapor in the flashed box here, and all of these are routed into the mechanical vapor compression, where they are superheated, compressed and superheated condition to the steam inlet condition, and that's the source of heat for the first effect. Then we have formed vapor by evaporation in one effect. We have flashed off vapor from the second effect to the third to the fourth, from the brine coming from higher to lower pressure. And there is flashed off vapor from effects, the flash boxes of effects number 2, number 3, number 4, who are joining the next effects 2, 3 or 4, or part of it is joining the foamed vapor to be entering into the compressor here. We have a couple of preheaters to preheat the feed from T cooling water to TF. The question marks here is representing the exercise that I want you to go through. I'll be leaving you for about 3 minutes so that you try to look at this carefully and think what these various question marks can be replaced by. For example, I'll just show you one of them right now. If, for example, for this one that we have on the top, let me see if I can insert text. Oh. Yes, for example, here that quantity here on the top is going to replace this question mark, is going to be basically, I'm talking about vapor leaving at effect number 4, so it should be D4 plus, there is certain quantity that has flashed off here, which is D4, and there is certain quantity coming from the flash box here, which is D-4. So this question mark that we have here is going to be replaced by this quantity that we have in front of us. Now, I want you to think of the rest of the question marks and what do they represent. So we have how many question marks we have here? There is 1 here, 2, 3, 4, 5, 6. Think of that and try to estimate what is going to be the quantities that should be placed corresponding to each one of these flash boxes. You'd like to do this together? Like work in teams so that you can think about it?
Maybe much better, Doctor.
Okay, so let me try to now I'll be forming like 3 rooms. The first room will have Abdullah Al-Azwari, Usama Al-Shahrani, and Saleh Al-Saffar. The second room is going to have Abbas Al-Yahya, Hussein Al-Yusuf, and Muhammad Al-Ghamdi. The third one will be Dawood Al-Haji, Hadi Al-Utaybi, Khalid Al-Shamrani. So I'm opening the rooms now. You must have been invited to join the rooms. Have you got an invitation for that? Usama Shahrani, can you join the room? Usama? Hussein? And Abbas Al-Yahya? Were you able to join the rooms or not?
Yes, but I couldn't see the your screen, so I came back.
Oh, I see. I'm not sure how that screen can be presented inside the rooms. It seems that it's not possible. Only Abbas has not joined his room number 2.
I can join it.
Okay.
Actually,
Doctor,
Yes.
we don't have the screen in the room.
Okay, you know what I can do is that I would make the screen available in Blackboard. Maybe, hopefully, you can be able to see it there.
Okay.
Doctor,
اتفضل.
if I leave the breakout room, I will directly be.
You will join us here.
Okay.
Actually, breakout rooms are going to be closed in 10 seconds from now. So I would assume that everyone is back here. And probably you have some time to think about it. Maybe you did not finish it all, but at least you have looked at the figure, and probably now we can just bring these results together here. For example, the question mark which is associated with number one here. So what is the quantity that's passing here?
D1.
D4 plus D4 small plus D-4.
Yes. Why not D1? Because D1 that has formed, it has just been formed here, so it's not coming here. The part that is condensing here basically is whatever is coming from there. Now let me use this. It does not have this this flash of light here because it's Word file. So anyway, basically, this quantity that we have here is the one that enters into the compressor. It is the one that has been compressed. It is the one which is being condensed here, and it is the same quantity which is reaching here. So at stage number one, the quantity here is the same as quantity right here, which is D4 that has been formed here by evaporation, small d4 by flashing, d4 in the flash box. This is the quantity which is being going through the compressor, and this is the quantity that condensed and reached here. What about 2? What has happened from this point to that point? At number 2, what you think is there? Let me, Khalid, you're raising your hand. You're raising your hand.
Doctor. Yeah. Can you hear me?
Let me start. I'll start in order. Khalid.
Yes. One question here regarding the what's come out, what comes out from the flashing.
Yes.
So from where exactly it's taken out? For example, if you look at the first effect, D-2, this is taken out from what exactly?
This is coming from the flash box that we have here, which is the flash box associated with effect number 2. Actually, this is coming because this D1 is leaving at the pressure P1. It will enter here at the pressure P1. It will condense at the pressure P1 because it's inside the tubes. And then after it condenses all, it will enter the flash box at pressure P1, while the flash box itself is at a pressure P2, so it will flash. The part that will flash is D-2. We take this flashed off vapor to join whatever is coming from the effect number 2 to enter the next effect. So this is D-2 basically.
And again, D-2 is a vapor, is a distillate.
It is vapor. It is vapor, yes. Whatever leaves the flash box from the top is vapor. So D-2 is vapor, D-3 is vapor. This vapor will condense inside the tubes of the next effect.
And the last question, the brine is not connected to the flash boxes, right? It's immediately connected to the second effect.
The brine, which is leaving effect number 1, is connected to the bottom of effect number 2, which is at a lower pressure. So part will flash here, which is D2, small d2. And then here we have a part that will flash, which is small d3. And here there is a part that will flash, which is small d4.
Thank you, cleared it.
Okay. So Dawood, Are you muted? I think you are muted.
Yes. The D capital 4.
Excuse me?
The answer
Yes, for D2, for question mark 2, yes.
as first one, but adding D1.
So
And
let me write as first one first. D4 plus D dash 4. This is what you mean.
yes,
Because this is the quantity that has reached here,
yes,
plus
plus the D1 minus D2 D slash 2. D
minus D dash 2.
yeah,
Oh, sorry, small d.
this is small d.
So this is what you mean.
Yes,
All agree on that? The quantity which is reaching here, basically the quantity that has reached here at 1 is going to remain with us, which is d4 plus d4, small d4 plus d dash 4. And then there's a quantity that will be added. The quantity to be added here will be d1, capital D1. There's no flashing inside here and there's no flash box associated with it. So it's got to be only capital D1 minus this quantity which is going to leave, which is d dash 2. Then, what about number 3? Saleh?
Yes, the first term, which is D4, D small 4, plus
D4 plus D4 plus D dash 4
4
plus
D1
D1
plus
plus
D2
D2
plus D small 2
D small 2.
minus D dash 3.
What about small d dash 2?
Eliminated with the previous one because
Yes, so here we have minus d dash 2. Here it will be minus d dash 2 plus d dash 2. So they will cancel out. And then we are going to have d minus d dash 3. Is that correct?
yes.
Is it fine for everyone?
Yes.
Okay, let's move forward. We have Abdullah Al-Azwari. At stage
Number 4, doctor.
number 4, yes.
D capital 4 plus
D capital
D small 4
D small 4.
plus D small dash 4
Now plus D small dash 4 and then
plus D1 plus D2 capital all
okay.
plus D small 2 plus D capital 3 plus D small 3 minus D dash 4.
Let's have a look at it. Now we have at 3 all of these quantities, and whatever is going to happen here, we are going to we have minus d dash 3 here and plus d dash 3, so the d dash 3 has cancelled, and you can see here that the d dash 4 also is going to cancel, isn't it? Because this term is here as minus and this term,
Going up.
Yeah. Yes.
so they cancel out. So basically we have d4 plus small d4 and d1, d2, d3, and small d2 and d3. And then what about at state number 5? What we have at 5?
D
Now
D3.
let's have somebody who did not join us in talking. Ahmed Hussein, are you with us? Please unmute.
Yes, doctor.
Yes, can you just at state number 5, what do you have here? What is entering here is coming from that entry here, which is what?
This is from state or affected
This is
3,
coming
right?
from state number 3, so it should be
D capital 3
and
D dash 2.
D dash Y2.
Oh, sorry, this is 3, but because the font is small. So.
Oh, D dash 3 and
D3.
And
D3, because inside state number 3, what has left is capital D3 and small d3, one of them by evaporation and one by flashing. And then we have D3 dash joining them, so that 3 of them are going to enter here. And then the 3 of them are going to leave at that point. Is it clear?
what is the last point? What is leaving this effect?
Now, the point here, what is leaving effect number 3 is capital D3 and small d3. Capital D3 by evaporation and small d3 by flashing here at the bottom.
Yes.
Okay, and then there's a flash box here, which is producing D-3 that will join them.
Yes.
So as they enter in here, whatever is going to leave will be that the 3 quantities that we have.
Okay.
Okay, D6, can we have Hadi?
Yes, doctor.
You know where's point 6? Here is it. It's hiding here.
Yeah, it's D capital 3, D small 3.
Yes, that's right. So now, as you see at the end, the product that we are going to get is going to be the combination of D1, D2, D3, and D4. So that was some sort of an exercise that I want you to get in, because you see, when you hear something or you see it in front of you, it's different than you doing it yourself. So I hope you have enjoyed this kind of activity here. What I may look at the moment is a modification that I would prefer to do in a system like this. We're talking about an MED system. In that MED system, basically you had effects. In these effects, we are having preheaters to preheat the feed. And we have flash boxes that are going to make use of the liquid leaving one effect as a vapor, and it will go to the second effect. And we have a down condenser. So this is the combination that we have basically for a multi-effect desalination system. Now let's do something. What if we move these flashing boxes inside? Then I forgot to mention, or what I did not mention, is that we have basically vapor which is condensing here. Vapor which is condensing here. And then we have vapor also which is condensing here. Isn't it what's happening? And then this is coming back as a product. And then the product is basically collected. So what I'm going to do is, number one, we're going to move the flash boxes inside the effects. Number two, we are going to eliminate all of these heaters and move these preheaters inside the effect. If I have a preheater here, I would move it inside the effect. What I did, it looks like a special case or a special type of an MED system, but the question is where actual heating is going to occur. I'm talking about water, seawater, which is leaving the condenser, and this seawater is going to enter it. It will be preheated in a tube bundle, which is basically this. And then it will be preheated in another tube bundle, which is basically, it was this. And then it will be heated in a tube bundle. What about the steam coming from a power plant? I'm going to make a special heat exchanger here. This is what we are going to call a brine heater. In the brine heater, what will happen? We are going to heat by steam from T1 to capital T naught. Capital T naught basically is our T maximum. And this is going to enter here at a higher pressure and temperature. The flash box is already there. So what will happen here? Flashing. Some vapor will go up. This vapor is going to condense on the surface, outer surface of these tubes. So I'm going to put a tray here to collect the condensate. So whatever vapor will go up here, it will condense here. By condensing, it will be preheating the feed, and then it will be collected as sweet water. So we have some sweet water collected here. And we have preheated the feed. And then the part that will not flash, it will leave this and enter to the next effect, which is at a lower pressure and temperature. So it will flash again. And some vapor will rise. The vapor that will rise is going to preheat the feed and then condense here. And then you can collect the condensate. And the vapor that will leave here is going to flash here, which is at a lower pressure and temperature. And then the vapor that will come up, it will condense here, and then you are collecting it here. And what you have here basically is you are having flashed off vapor that will enter to the condenser. And in the condenser, what will happen? It is going to preheat the feed, which is going to flow here. So this is m dot feed plus m dot cooling water. So it's a rough sketch. By this rough sketch, I wanted you to look at the MED as the original kind of layout. Out of the MED, we came up with a modification, and this modification that you have just seen now is nothing but the multi-stage flash desalination system, which is the last mode of conventional thermal desalination that we are covering. That mode of desalination is the one that had started in 1955 in the area by the first MSF plant that was built in Kuwait, 1955, by American company, which is Westinghouse. The unit has started operated, and MSF so far is the largest contributor to desalinated water in the Gulf area. Saudi Arabia, Kuwait, Bahrain, Emirates, Oman, they are all having the majority of water so far up to today is coming from this system, MSF systems. What's good about the MSF systems? We don't have tubes of bundle of tubes inside here for heating, but we have only the preheaters that are inside. In this preheater, we have seawater coming from the seawater temperature, heated to the feed temperature. And then as we are moving from one effect to the other, the feed temperature is being increased until we reach here for the highest feed temperature. We enter it into a heat exchanger. Normally it's a shell and tube heat exchanger. We heat it to the top brine temperature. So heating here occurred in one unit. And then flashing and flashing and flashing and flashing. So the very hot seawater does not pass in tubes anymore, but it is just flashed in the pool of every one of these stages. Those units that are being heated, actually, they can be heated from a temperature of about 40 degrees centigrade up to a temperature of about maybe between 70 to 90. And this is only, we are recovering heat from the steam which is generated or the vapor generated in every effect. The vapor does not pass outside the tubes here. Seawater does not pass outside the tubes. Seawater is not sprayed, but the seawater is just passing inside the tubes. And for cleaning, they have small bowls, just as the size of the ping pong balls that you know, they are soft, and they send these balls inside the tubes while the whole unit is operating. So you do cleaning while you are operating. And this is one of the good features of the MSF. So MSF is our next topic. On Wednesday first, as we did earlier, we're going to start with a single stage flash. And then once we understand fully how the system is operating, we're able to write the first law equation for it and the mass balance, then we are going to move to the multi-effect desalination system. So that was just a brief introduction to the topic that we are covering next time. And that's it for today. We'll see you next time, inshallah.
Thank you, Doctor.
شكرا يا شباب.
يعطيك العافية دكتور.
الله يعافيك. شكرا جزيلا يا شباب. شكرا.
Doctor,
تفضل.
I didn't get the modification of how we convert from MED to MS.
Actually, it's not a conversion, but I just wanted to show you how close they are to each other, and as if الأصل هو ال MED مع شوية modifications وصلنا لل MSF. How these modifications are done, basically the preheaters has been moved to the top inside each stage. The
Yes.
flip boxes has become inside the stage, and we remove the tube bundles where spraying occurs.
How the
And
heating will.
heating in every effect, we only heat at a brine heater or a heat exchanger before the effects.
Okay, so the preheater at T0 reduce flashing or
This is actually the preheater is going to heat the brine from this temperature to something like 115 or 120 degrees centigrade currently as of the next technology. As of the current technology now, this top brine temperature is something between 115 to 120. It will enter here into and this is normally at a pressure higher than atmospheric pressure. It will enter effect stage number 1, which is at atmospheric. So there is a reduction in pressure, it will flash. The remainder that will not flash will go to the next effect, which is at a lower pressure, so it will flash.
okay.
That will not flash will go to the next effect, it will flash, and we'll keep on repeating this process until the last effect whose temperature is going to be about 40 degrees centigrade, which is T cooling water plus 10, as we did earlier.
So the preheater flash heated by flashing.
The preheater is this. You mean these units, these parts here? They are heated by the flashed off vapor, the vapor that comes by flashing. It will heat the water inside, and meanwhile it will condense. And the condensate is our product.
Okay.
Is it clear now?
Yes.
طيب, okay.
Thank you.
الله يعافيك. شكرا جزيلا.